Well, thanks for the introduction, and thanks for the invitation, John and Martin. I've really enjoyed my days here. Let's get started. So the work I'm going to tell you about is squid microscopy. Squid is a loop of superconductor that has at least one, but in this case two, weak links that form Josephson junctions. The characteristics of the squid depend very sensitively on the amount of magnetic flux which is threading through it. I think I have a little symbol here. The periodicity of the characteristics depend on the superconducting flux quantum, which is a small number. To scale things, there are something like 20 million flux quanta passing through everywhere from the Earth's magnetic field, and we can measure 1 part in 10 to the 6th of the flux quanta per second. So we're measuring something like 1 part in 10 to the 12 of the Earth's magnetic field. This is sort of a diagram of a standard squid. We sort of modify things for microscopy. What we do is we sort of stretch it out and give it a twist so that there are two pickup loops there and there. The twist means that it's insensitive to a non-spatially varying field. So we want to be sensitive to what's going on in the sample. We put shields on it. In our case, the shields are made of superconductor, and the shields actually encase the leads in a coaxial structure so that it's very insensitive to magnetic field, except for where the pickup loops are. One of the pickup loops is brought close to the sample. The other pickup loop is several tens of microns typically away from the sample, so it doesn't really see much in terms of what's going on with the sample. And then we also add a modulation coil. What this does is the characteristics of the squid are sinusoidal in the flux. What we do is we bias it using this modulation coil, so we're on the steepest part of the response curve, and this maximizes the sensitivity. It also allows us to use a flux feedback scheme which linearizes things, so that we really have a very good idea of how much flux is passing through the squid. These sensors also have a field coil wrapped around each of the pickup loops. And what this does is allows us to locally apply a magnetic field and then see the response. Since the one pickup loop is so much closer to the sample than the other, what we see is actually the difference in the response of the sample with respect to nothing. And then the current through the field coils gives you an applied field, and then the response is a susceptibility. So we do scanning susceptibility. So in our devices, the pickup loop, this is an optical microscope image of the pickup loop field coil area. We polish the substrate. The squid is made of niobium, and it's on a silicon substrate. We polished the substrate so it's very close to one of the pickup loops, and then adjust things so that the squid is very nearly parallel to the sample. So here it is. The squid is touching the sample. You can see the image, the reflected image of the squid in the sample. and we adjust things so that it just barely clears the wire bonds. So we want as shallow an angle as possible, and we can get typically a few degrees. Then the spacing between the pickup loop and the sample is this distance, which is typically 10 microns, times the sine of that angle. So we're typically spaced about a micron above the surface. The devices we use have a flux sensitivity of about 2 microphi-knots per root hertz. At 10 hertz, there is some 1/f noise. This corresponds to a current sensitivity of about 5 nanoamps per root hertz. So we can spatially resolve a current of about a few nanoamps with a spatial resolution of a few microns. The squid microscope has been used for a wide variety of applications, and I've just sort of flashed some of them up here. It's been used for determining the pairing symmetry in the high-temperature Coupe superconductors. It's been used to place limits on the spontaneous currents in strontium ruthenium oxide, which is believed to be a P-wave superconductor. It's been used to measure the persistent currents in normal metal rings at low temperatures, and it's been used to show that the transport in the two-dimensional electron layer at the interface between strontium titanate and lanthanum aluminate can be quite inhomogeneous. We believe that the transport is dominated by transport along the domain boundaries in this material. But today I'm going to be talking about topological insulators. A topological insulator is material that is insulating in the bulk, but conducting on the surface. An example is cadmium telluride, mercury telluride, cadmium telluride quantum wells. If the mercury telluride is sufficiently thick, then it's possible for the highest level valence band to be above the lowest level conduction band. We call this band inversion. If that condition is satisfied, then you can get very interesting effects. In particular, if you calculate on this right column the band structure for a cylindrical sample with this quantum well structure, if the thickness of the mercury telluride is below a certain critical value, then you have sort of a normal insulating gap between the valence bands and the conduction bands. But if this thickness is above that critical value, then you not only have this insulating gap in the bulk, but you also have 2 surface states. The surface states in a 2-dimensional material like quantum well are actually edge states, and they have 2 strange properties. One is that the conductance is quantized. You get 1 E squared over H unit of conductance per channel. The other thing is that the spins are polarized. That is that electrons traveling in one direction have 1 spin polarity. Electrons moving in the opposite direction have the opposite spin polarity. This is called the quantum spin Hall effect, and it's been confirmed in this system by using bulk transport measurements. In particular, if you gate the sample, if you apply an electric field to it to change the level of the Fermi level so that it goes in between the conduction band and the valence band, then you have quantized conductance. If the sample is sufficiently short, turns out that scattering is such that if the samples are more than a few microns long, then you lose this flux quantization, conductance flux quantization. The work I'm going to be telling you about was first was done by Katja Nowak, who is a very talented postdoc in Cam Mohler's group at Stanford. So she took a quantum well sample, as I've been describing to you, and fabricated a Hall-bar geometry into it. So you have two current leads that run current through the sample, but it's also gated. There's a gold electrode separated by an insulator on top, so you can apply an electric field and change the level of the Fermi level. The sample contacts are on the same side of the sample, so that Katja can bring in the squid from the other side and get it in there without running into the contacts. As you gate the sample, as you change the Fermi level relative to the band gap, what you find is that if the Fermi level is either in the valence band or in the conduction band, then the conductance through the Hall-bar is fairly standard. This is just a solution of Poisson's equation for a standard Hall-bar. Excuse me. However, if you bring the Fermi level so it's in between the conduction band and the valence band, this freezes out the bulk conduction, and you get only edge conduction. So the conduction runs around the edges of the sample. So that's what we want to try to image. You can image currents in a sample because the sample generates magnetic fields. The magnetic fields are given by the Biot-Savart law. We could put a pickup loop in front of or on top of the sample, and some of the magnetic field couples into the pickup loop, and then the flux through the pickup loop is equal to the convolution of the magnetic field times a point spread function for the device. You can work backwards. Once you know what the magnetic flux above the sample is, then you can deconvolute this this relation and get the two-dimensional current density from the flux image, and I'll show you some images like that. And the selling point is that because the top gate doesn't interfere with the magnetic fields, you can do this for a top gated sample, and that's a lot easier than having a back gate. So if you apply a voltage to the gate, again, you're adjusting the Fermi level relative to the gap. The resistance has a peak when the Fermi level is in the gap, and it's lower on either side. These Hall-bars are long. They're about 50 microns long, longer than the mean free path of the device, so that this peak is much bigger than E squared over H, or 2E squared over H. Well, it's H over E squared, I guess, in resistance than you expect for quantized conductance. Nevertheless, the current should be going along the edges. So these are images that are taken when the Fermi level is either in the valence band or in the conduction band. And let me spend a second to explain the color maps that I'm going to be using. So here, blue is magnetic flux going up through the pickup loop. Red is magnetic flux going down through the pickup loop. And white is sort of zero. So here there's a fairly gradual gradient of the magnetic flux as you pass your squid across the Hall-bar. If, on the other hand, you put the Fermi level in the gap, then you freeze out the bulk conductivity, and you can see there's a very sharp white line here that corresponds to a sharp drop in the magnetic flux at the top edge, and a somewhat more diffuse drop at the bottom edge. You can sort of think about what's going on by just using a simple wire model. In one case, if the let's just do the whole thing. Whoops, that was a mistake. In one case, when the Fermi level is either in the conduction band or the valence band, then you can think of the transport going along an array of wires, and you get a fairly diffuse distribution of fields. If, on the other hand, the conduction is being carried by the edges, you can think of that as being two wires, and then you get sharp peaks and overshoots at the edges. It's somewhat more intuitive to do this inversion I was telling you about. So here on the left-hand side is a field profile. In the middle is the component of the current in the x direction, the horizontal direction, and on the right is the component of the current in the y direction. So, and this is with the Fermi level in the conduction band. So the current goes down, it goes across, and then it goes up. But the going across is again fairly uniform in the sample. If you put the Fermi level in the gap, then what you see is very localized current along the top edge. So it goes down, it goes across the top edge, goes up, but then it also sneaks around the outside of the sample because it has to flow along the edges. The bulk conductance is pretty well frozen out. You can also tune the Fermi level through the gap and make a little movie. So this little dot shows you the resistance of the sample. So right now I'm freezing out the bulk, and now you're getting both bulk and surface. And you can see that one thing that should be pointed out is that there's both bulk and surface conductivity happening at the same time, say right there. And also, of course, the imaging shows you about inhomogeneities, which bulk measurements don't do. Yep. This is probably at something like 200 milledegrees. This was done in a dilution refrigerator. I'll show you some temperature dependence a little later. If you run a control sample, remember I told you that you have to have the thickness of the quantum well above a certain critical value to have these topologically protected states. This is a sample where the thickness is less than that value, and in all cases, then the magnetic fields are fairly diffuse. In order to sort of quantify the relative contributions to the current from the bulk and from the edge, what Katja did is fit cross-sections through the data to a three-component model. And so there's a component to the top edge, to the bulk edge, to the bottom edge. When you do that, what you find is that if you look at the fraction of the current carried by the three different things, top, bottom, and bulk, what you find is that as the bulk is killed by putting the Fermi level in the gap, the contribution from the top edge and the contribution from the bottom edge grow up to make up for that loss in conductance. However, if you take a simple model in which you assume that the three components have an effective resistance and plot the resistance instead of the amount of current, what you find is that the bulk resistance gets very big when you put the Fermi level in the gap, but the the current through the top edge is really relatively independent of gate voltage. So I actually found this a little bit surprising, that the edge conductance really doesn't care about what's going on with the bulk conductance. This is also true if you look at the temperature dependence. So this is going from 4.5 degrees to 20 degrees. Yeah, I guess actually this temperature dependence was done in a different microscope because it's hard to get a solution refrigerator up to 20 degrees. Trust me, not much is going on between 4 degrees and 200 milledegrees. Anyway, if you have the same sort of three-component model, what you find is that the bulk conductance, this is resistance, the bulk resistance falls exponentially as the temperature is raised. But the conductance of either the top or the bottom edge really doesn't change much as a function of temperature. And I think that's saying something about the mechanism for scattering of the edge states. And in fact, that's an important thing, because if you want to make devices, you want to make them so that you can make them bigger than a micron. So that's an important thing. It's been predicted that if you put a superconductor in contact with a topological insulator, that lots of interesting things will happen. But in particular geometries, it's been predicted that you should get Majorana bound states. These are zero energy. They're called Andreev states that are trapped in between the two superconductors. And in particular, it's been predicted that there should be a relationship between the Josephson current and its phase, which is different than the conventional one. It should go like the phase divided, sine of the phase divided by 2, rather than the sine of the phase for a conventional Josephson junction. There has been some evidence for Majorana bound states in these sorts of systems. In particular, if you have, this is an indium antinomide nanowire on top of a niobium tin nitride superconductor. The indium antinomide has a strong spin-orbit coupling, and you can apply a sufficiently large magnetic field parallel to the nanowire to make the Zeeman splitting between the states larger than the induced superconductivity in the nanowire. If you do those three things, then it's been predicted that you will have a Majorana bound state at the two ends of the nanowire. And in this study here, they looked at tunneling into the nanowire and saw zero bias anomalies appear at finite fields consistent with the predictions for a Majorana bound state. There's also been some evidence for a sine phi over 2 current phase relationship. This is some work done with, it's indium antinomide in a weak link geometry. They shown microwaves on this. It makes a Josephson weak link. If you apply microwaves to it, you get the AC Josephson effect, which should give you steps not only at integer multiples of h nu over e, but also half-integer multiples if you have these Majorana bound states. And these half-integer steps can be suppressed by applying a magnetic field. There are also hints of a strange Josephson current phase relationship just in studies of junctions. So this is a junction composed of the conventional superconductor aluminum the transport going through bismuth selenide. Bismuth selenide is a 3D topological insulator. And so this is David Goldhaber-Gordon's group at Stanford. What they did is they took a flake of the bismuth selenide and photolithographically defined a junction. What they found is that they got Josephson-like current voltage characteristics, but they had very strange behaviors. In particular, the Josephson current, the critical current, actually decreased as the width of the junction increased. Also, the Fraunhofer interference patterns, which should look like this solid black line. So they're applying a magnetic field perpendicular to the junction, and they're looking at the critical current. What they saw instead is this red, very strange characteristic. In trying to understand what was going on, they found that they could explain their experiments by assuming that the current phase relationship, instead of being sinusoidal, has a strong peak at current phase drop across the junction of pi. So the work I'm going to be telling you about now was done by Ilya Soshnikov, who's also a postdoc in Cam's group. And what we did was we decided to measure the current phase relationship in these types of junctions directly. Turns out that this can be done quite simply with a scanning squid microscope using a technique which was first introduced by Jackal et al. At Bell Labs in 1974. Essentially, what they did is they put a squid next to a ring, which included a junction, and by applying a flux to the ring, it induces a circulating supercurrent. What the squid microscope does is allows you to put the squid anywhere you want relative to the ring. So in particular, if you put the sensor directly on top of a ring which is composed of conventional superconductors and then a junction which has the current going through the topological insulator, the field coil generates a flux which goes through this ring. The ring is superconductor. It tries to expel that flux. It does that by generating a circulating supercurrent. If the inductance of this ring is sufficiently small, and in fact it is, then there's a simple relationship between the phase drop across the junction and the flux you supplied. So it's just 2 pi times the applied flux divided by the superconducting flux quantum. You can tell how much current is going around the ring because through the Biot-Savart law, it couples flux into our pickup loop. So we have both the phase and the current, and we can get the current phase relationship really quite directly. Why is this a good thing? One is that you can make measurements on one junction rings, and I'm going to tell you in a few minutes why that's a good thing. You can optimize your geometry, so we actually chose the ring diameter so we get the best signal to noise from our squid. And you can do many nominally identical samples, or you can vary parameters, as I'll show you in a bit. So what do we expect to see? What we expect to see is that for a conventional Josephson current phase relationship, so I've just plotted this. So this is the current across the junction as a function of the phase drop. It goes like the sine. Then what you expect to see is that if you have a small product of the inductance times the critical current, which is in fact the case in our samples, then you expect to see something that looks very sinusoidal. It's only when you have a large inductance that things start to get a little weird. If you have the current phase relationship that the Goldhaber-Gordon group proposed, which has a sharp peak at a particular value of the phase. This would translate to a sharp peak in the circulating supercurrents at a particular flux through the ring. So qualitatively different results should result. In a topological insulator with the Majorana bound states, turns out that there are two allowed these Andreev bound states, which are bound in between the two banks of superconductor. They're pi phase shifted with respect to each other. So I've drawn this as a solid line and a dashed line. If it is not allowed for the Majorana bound state to hop on and off of the junction, then what you'd expect to see is a current phase relationship which has 4 pi periodicity, either the solid line or the dashed line. If, as seems more likely, that you can have switching, maybe thermally excited switching or from noise or something, then the energy phase relationship should follow the lowest allowed one, and then you recover something that's 2 pi periodic, but it's asymmetric. And it's that asymmetry which is a possible signature of Majorana bound states. What happens if you have both the conventional current phase relationship and this unusual one? We can model that by having a linear combination of the two dependencies, and then that translates through to something that at first skews the current phase relationship a little bit, and then finally, for a large mixture, you get bumps. This is for a single junction ring, and this is in contrast to what you expect for a two-junction ring. For a two-junction ring, this group at the University of Twente showed that what you expect to see is something that looks very much like a conventional interference pattern for a ring, even if you have these strange Majorana states in the junctions in the ring. The only difference is that you get some slight changes in the amplitude of the modulation of the critical currents. So that's why one-junction rings and squid microscopes are better. So the experimental results looked like this. So first I'm going to tell you about two systems, one with bismuth selenide, which is a 3D topological insulator, and then I'll tell you about mercury telluride, which is a two-dimensional topological insulator. In the case of the 3D topological insulator, what Ilya found is that as he swept the current through this field coil, he saw a sinusoidal flux threading through the pickup loop. But there was also a linear background to the response. You can decompose the response into the two components, the linear background and the sinusoidal component, and actually image what's going on as you vary the position of the squid relative to the ring. And what you find is that the linear component gives you something that looks like Pac-Man. So you have a ring, but there's a bite eaten out of it, and that bite corresponds to the position of the junction. If you look at the sinusoidal component, it has a cylindrically symmetric response. And so what we think is going on is that this linear component is just Meissner screening from the aluminum ring itself. And the cylindrical component, the oscillating component, is due to the circulating currents going around the ring. So it's Meissner screening circulating currents. And so from now on, I'm going to concentrate on the circulating currents because they tell you what's going on in the junction. Oh, yeah. And the bottom line, and this took out about 10 slides from my talk, is that this is very sinusoidal. It's very conventional. And what we think is going on is that if you look at photo emission results for the bismuth selenide, the Fermi level is actually in the conduction band, so that there are lots of bulk states, and they're just sort of swamping out anything that might be going on from the topological insulators. How are you doing? I'm doing fine. The second experiment, set of experiments, uses a two-dimensional mercury telluride topological insulator. So how this is grown, this is done by the Molenkamp group at Würzburg. And what they do is they grow mercury telluride on cadmium telluride. It's, there's a lattice mismatch, and so the mercury telluride is strained. And it turns out that what that does, it tends to pin the Fermi level in the insulating gap. So in this case, you're more likely to see effects from topological protection. And in fact, you do. So this is the current phase relationship that Ilya got. It's a little bit hard to see, but there are a bunch of symbols there, little circles. And superimposed on top of that is the Josephson sinusoidal current phase relationship. And what you're supposed to notice is that the experimental current phase relationship is skewed. It has more current at higher phases than at lower phases. And it turns out this is what you expect for a topological insulator. Yeah, and this is necessary but not sufficient to show that you're actually seeing results from the topological insulator physics. Because of because we're using a microscope, you can not only look at one ring, but you can look at lots of rings. So they fabricated 50 rings on the same sample with different junction lengths and widths, and studied them all using the squid microscope. There have been a number of predictions for what the current phase relationship should look like for a junction between a conventional superconductor and a topological insulator. And it's fair to say that they all predict a skewed current phase relationship, but it's also fair to say that none of the theories that we've found can model all of the effects that we've seen. In particular, one of the series that Ilya ran is that he looked at a set with different junction widths. So if you look at these rings, they all have the same average diameter, but they have different wall widths, and this corresponds to different junction widths. Then what you find is that as the junctions get wider, the critical current gets bigger, but in fact, all of the experiments showed a skewed current phase relationship. You can quantify this skewing by a number of ways, but one of the ways that Ilya used was to fit it to a linear combination of a conventional current phase relationship and a sine 2 phi current phase relationship. And then this coefficient of the second component is called the sine 2 phi component. What he found is that the critical current of these junctions increased as the ring widths increased, but not in a linear fashion. So I would have expected that as you went to thinner and thinner, less wide and less wide rings and junctions, that it would extrapolate to zero. But that's not what you see. And in fact, yeah, it actually fits pretty well to a parabolic dependence. I mean, they're scattered, but it's not too bad. We have no idea why that should be. The measure of the asymmetry, the skewness of this current phase relationship really doesn't change much with ring width. And this is perhaps understandable. If you look into some of these theories, in particular this one by Tkachov, what they do is, first they calculate what the Andreev bound state should look like for an infinitely narrow junction. And what they find is what I've drawn before. You have two energy states, two Andreev bound states shifted by each other with respect to each other by pi, but they the states cross each other. As you go to wider and wider junctions, you can start to get off-axis transport through the junction, and this tends to open up a gap between the two allowed Andreev bound states. It turns out that the Josephson critical current should be proportional, maybe I've drawn it down here, should be proportional to the derivative of the energy of the bound state with respect to phase summed over the occupation of the bound states. So you expect to go from something which looks pretty sawtooth-like to something which looks more rounded as you go to wider junctions. What we see, in fact, is just the opposite. That as you go to wider junctions, the asymmetry gets bigger. And this dashed curve is sort of a cartoon drawing of what you might expect to see. If you go in the other direction, so instead of making the junctions wider, you make them longer. You get these results. So as you might expect, as you get longer junctions, the critical current gets smaller. The superconductivity has to overlap over a longer range, and it's more or less exponential. But if you overlap these curves, so scale them so that they overlap, they really look very much the same. The skewness is very much the same. So the current phase relationship, except for the scaling factor, doesn't seem to change much with length. Again, going into the theory literature, we found that what they expect is that if you have a junction length which is smaller than characteristic coherence length of the scattering, then you get a fairly skewed current phase relationship. As you go to longer junctions, then you expect to see a more sinusoidal current phase relationship. It's at least consistent that it could be that what we're seeing is that our junctions are not long enough, that we're in the limit where we're less than a coherence length, and that tells you something about what the coherence length is. I'm just about done. A little fast. Let me summarize. I hope I've convinced you that the squid microscope is a convenient tool to image transport, and it's pretty good. It resolves things on a micro scale and has sensitivity on the nanoamp scale. we've demonstrated that in a two-dimensional topological insulator, the current flows along the edge when you're in the quantum spin-Hall regime. That is, when the Fermi level is in between the conduction band and the valence band. The bulk conduction and the edge conduction can happen under the same conditions, but they have very different gate voltage and temperature dependencies. And I think that should tell you something about the mechanism for scattering of the edge states. In junctions made with the three-dimensional topological insulator bismuth selenide, you have very sinusoidal, very conventional current phase relationships. And that may be because the Fermi level is in the conduction band and you're dominated by bulk states. If you do the same experiment with mercury telluride junctions, they have asymmetric current phase relationships, which are nearly independent of length. And that, I put a question mark here, that may mean that the junction length is comparable to the coherence length. So we're talking about coherence lengths of Cooper pairs in the topological insulator comparable to the length of the junctions, which are some fraction of a micron. And finally, in these junctions, the asymmetry is almost independent of the width, sort of opposite to what you might expect. And maybe that means that you have, in addition to the topologically protected states, maybe they're also topologically, non-topological. Yeah. And guess what I mean there is non-protected states. Topologically non-protected states. Yeah, so Cam Moeller's the boss. She's the head of the lab. And the two postdocs who led the studies that I've told you about are Katya Nowak and Ilya Soshnikov. This is a portrait of Cam's group. Right now it's 6 postdocs and, I'm sorry, 3 postdocs and 6 students. And trust me, they don't always look that neat. Yeah, and the work was done by, the scanning squid microscopy was done by, in Cam Moeller's group at Stanford. The samples were produced, were fabricated by David Goldhaber-Gordon's group at Stanford using material grown by the Molenkamp group at Würzburg. And we've had theoretical support by Xiaosheng Zhang and Zhao Yangji. I'm sure I've completely destroyed their names. Thank you.